Thank you so much for coming, by the way. I really appreciate you all choosing to spend your time here with me. It really does mean a lot to me. I mean, actually, one, I know you don't really have a choice because there's no other talk right now. And two, I know you are all secretly here to have a good seat for the Guy Steele talk that's coming next. But that's okay, because that's why I'm here too. So anyway, I appreciate you just the same. Thank you also to Clojure, to our sponsors, to Cognitech, to the venue, to everyone who's helped make this possible. So thanks very much. This is a computer talk, mostly. So you have to start with 0. So hello, I'm Eric. I tend to speak very quickly, particularly when excited or nervous, and talking about machine learning and Clojure and giving talks makes me both excited and nervous. So I will try to slow down, but if at any point I'm kind of going off the rails or speaking way too fast, just kind of like make a big, some kind of signal, and I'll try to bring it back down. I'm going to talk for about 35 to 40 minutes. If it's closer to 35, we'll have time for questions at the end. If it's closer to 40, I won't take questions, but feel free to come find me later on tonight or at the party or anything like that, and I'm happy to try to answer any questions that you might have. So like I said, my name's Eric Weinstein. I am a director of engineering at Fox Networks Group in Los Angeles. So the program says Hulu. That was true up until a couple months ago. I now am building a team and a platform over at Fox. We are doing this for all of our television content, including The Simpsons, Archer, National Geographic, Fox Sports, and more. And yes, we are hiring. All that information and some more is in this human map that I made for some reason. I write a lot of JavaScript and Go at work. I write a lot of Clojure on the side. Although, as Rich mentioned, there are tons of people trying to sneak Clojure into their work environment, and I'm definitely one of those people. I've been writing Clojure for a few years now, and I recently wrote this book over here, Ruby Wizardry, that teaches Ruby to 8 to 12-year-olds. Ruby's like Clojure, right? I feel like those are kind of the same. That's a joke. So if you are interested, please do come find me after the show. The good folks over at No Starch have set up a promo code. The book is 30% off from their website with the ClojureConch 30 promo code, so feel free to snap a picture. This slide will be up at the end again, and that's at www.nostarch.com. So thanks also to No Starch. Some of you may have been at Euroclojure last year in Bratislava, and if so, you may remember another machine learning talk that I gave, and wondering which I had a cup of coffee like this one that I perpetually kept almost drinking. And there was, in fact, there were a lot of jokes in the Slack channel and numerous bets about when I would actually drink it, and then jokes about using machine learning to predict when I would actually drink it. So this is a bit different from that talk. We're not going to be doing classification of images and things like that. We're going to be generating text, but the coffee bit is probably going to be the same. This is not a long talk, but I do think we benefit from having a roadmap. So I'm going to start by talking about poems about technology, and we'll talk a little bit about T.S. Eliot's objective correlative. Then we will selfishly look at a poem that I wrote that is about machines. Then we'll move on to a poem that I wrote that is also a Clojure program. And so there's something for the human reader and something for the machine reader. And finally, we're going to look at a couple different ways to produce poetry using Clojure. One of them using Markov chains, the other using a recurrent neural network. How's this speed? Is this speed good? Excellent. Thank you. All right, so we're going to kick it off with a poem about the machine. So a finite state machine, going back to the name of the talk, is a model of computation that can be in a finite number of states, and only one of them at a particular time. An infinite state machine is like a finite state machine, but with an infinite number of states. So this is sort of like all the poems, or the universe, or something Turing equivalently romantic. So that's big R romantic, because we're going to talk about John Keats in a bit too. Some of you are probably thinking, hang on, I was pretty sure I signed up to come to a Clojure conference. So why is this guy going to read us a poem about computers? Well, let's take a look at what T.S. Eliot called the objective correlative, and I'm going to quote from Wikipedia. It's the artistic and literary technique of representing or evoking a particular emotion by means of symbols that objectify that emotion and are associated with it. So before I wrote poems for machines, which I think most people call software, I wrote poems for humans, which I still do sometimes. I used to give a whole bunch of readings, and so I like to set expectations. So here you go. I'm going to read exactly one poem. It's going to be called Memory Leak. It's not really about a memory leak per se, but poetic license, which is also the license I'm going to use to open source this. And that was a dumb joke. Thank you for laughing. So it's going to take about 1 minute to read, probably actually less than that. Keep an eye on the images/symbols, and thank you for your patience. So, memory leak. The machine stays up all night writing poems, smoking some. It spawns a billion threads of execution, little tales it tells itself. In tale 0, it sails from island to island in an archipelago linked by green arrows of algae. In tale 1, it is a blue fork of lightning whose ends reach into the head of every child in the neighborhood and install imaginary friends, a sheep, a robot made of bottle caps. The machine constructs these artificial histories, but never deletes one. One memory runs into the next. Bioluminescent algae fill the neighborhood pools. A robot sails for the new world in a stiff breeze. The humans wake to find 1 billion machine poems overflowing the hard drive. The last one reading, I would grow human teeth of my own and dissolve them. I would send signals directly into your heart. So this poem first appeared in the final issue of Court Green, which is a literary journal, and that was in the spring of 2015. So why does this matter? Why did I bother reading this? What is this poem for, right? Which is, I think, something I really appreciated about Rich's keynote. This all matters sort of, I guess, as per the objective correlative, and that these images stir us to action. These objects have emotional weight, and they make us feel something. Similarly, poems for the machine move the machine to action. We provide instructions, and the machine complies. So I think that's going to be, keep that in mind as we look at, especially the next few slides with a poem and a program that are the same. All right, so now that that's all over with and we don't have to listen to poems anymore, let's take a look at something that's actually a program. As I mentioned when we talked about Eliot, there are sort of these notions of objects, these notions of symbols, and they're an opportunity for what I like to think of as dual attention, this sort of doing two things at one time. There are dual narratives, there's sort of the tension between the line and the sentence, the relationship between a poem's title and its text. And I think that this speaks to a lot of the parallels between poems and programs. Above and beyond syntax, poems and programs both have style, they have idiom, they have line breaks, and beyond even that, they cause something to change in the world. They result in an action or a change in state. So we're going to add a new dimension to this discussion, which is what happens when those dual attentions are one story for the human reader and one story for the machine reader. And this is a poem and a program called REM Cycle. And I apologize if it's a little bit hard to read. This may remind you a bit of Shakespeare. There's a Shakespearean quote at the top. We'll come back to Shakespeare a little bit later in the talk. I sort of stole a lot of ideas from him because when you're a poet and a programmer, you are also a thief, which is good, I think. It's also tough to make a pun with this file name. It's REM Cycle, but there's the CLJ extension, so the J is silent. So I'm just going to read this really quickly. Defog the window to withstand the presence of ghosts. Let us know that they all lived, and the window is open. Us and the window. Define for me, let the ending be happily ever after. The ending be, or me. Deforest, now, the ending is written on the tallest tree. Let me be ogre, able and open. Hands ineffable. Oh, strange, we are haunted. First me, first fable. And does anybody know what the output of this poem would be? And if you can read it, the strings that are in here are kind of a hint. You can shout it out if you think you know. That's all right. I'm not going to do a demo. I'm not going to run it because those always go horribly wrong. But the output of this is know that they all lived happily ever after, which is super trite, but is the most meaningful thing I could get the machine to produce. And then you kind of note the optional commas, the syntactic flexibility of Clojure. Sort of imagine what we could do if we were using, macros and additional, like the full arsenal of Clojure's flexibility. Note also that I pronounce this slightly different than it's written, but I think, again, you can sort of apply a poetic license there. So we've seen a poem about machines. We've seen a poem that is a machine or is readable by machines. And now we're going to turn our attention to what I think everyone is really here for, which is to see how we can get Clojure to write poems for us. Because that would be awesome if I didn't have to write my own poems all the time. So we're going to use two different techniques and two different training corpuses to produce these results. The first one is Keats's 1817 poems. The other are the works of Shakespeare. We're going to use a Markov chain for Keats, and we'll use a recurrent neural network for Shakespeare for reasons that will become clear in a minute, why we have two different models and two different training corpuses. So the first one, like I said, are the 1817 poems by John Keats. It's about 2,000 lines, 13,660 words, and just shy of 80,000 characters. I picked Keats and not, say, Eliot, who might make more sense since we were talking about the objective correlative, mostly for copyright reasons. I wanted to make sure I could give this talk and put things on GitHub. And I did not pick Shakespeare for this one because narcissism, which I will explain in a minute. This speed is still good? Cool, all right. I'll stop checking in, just stop me if I start going off the rails. So a Markov chain, which is the model we'll see in a minute, is a stochastic, memoryless process. It's effectively a random walk. You tell the machine, hey, here's a couple of words, and then see what comes next. And the Markov chain is a Markov process that obeys what's called the Markov property. And the essential idea here is that your next state depends only on your current one. So there's no memory, there's no past actions. You can sort of fudge it a little bit by kind of baking arbitrary amounts of history into your current state to produce the next one. But it's effectively a random walk. And here what we do is we pick a couple words, and then we jump to the next one, and we kind of crash around the training corpus and see what we produce. And in this case, after reading the 1817 poems by Keats, we got this prose poem by a machine. I'm not going to read this to you. I might read little pieces. Again, I apologize if it's hard to read. I had to trim it down a bit because the machine was verbose. But I will leave the slide up for a minute so you can kind of get the gist. The interesting thing here that I really like is the poems from 1817 contain the name Eric exactly one time. But somehow, in my dozen or so Markov poems, the robot put my name in there. And like I said, because narcissism, I decided to stick with this and not switch over to Shakespeare. So, yet this happy burthens, Eric. I echo back each sting thrown by thy vigils. Keep monk's boughs pavilioned where sheeted lightning plays, et cetera, et cetera. And you can already see, it's kind of like English. I mean, it is. It sort of makes sense, but not really, right? But you could maybe give this to a middle schooler and say, this is a poem by Keats, and they'd be like, I don't get it, but yeah, that looks like Keats, right? So, which is, I think, very impressive, considering the code is maybe 15 lines. It's really just kind of tear apart the text, figure out what came before, and make a jump to what comes next. And you can see I haven't really done a lot here in terms of line breaks, in terms of, you can see the capitalization kind of restarts when it jumps to a new sentence. I've gone back and forth about whether I want to sort of continue to process the text and say, well, maybe the robot is smart enough to put in line breaks, maybe the robot is smart enough to change capitalization or start sentences or lines with capital letters as appropriate. Or maybe we say, you know what, it's okay for a human editor to take the machine poem, clean it up a little bit, and say, look at this collaboration. This is, in fact, what I did a few years ago with a Ruby program I wrote called Recurrent. And Recurrent basically would generate tons and tons and tons of quote-unquote poems, I would convert them into real poems, and then I would send them out to be summarily rejected. So, but it was a lot of fun. It's kind of like pitching conference talks. Anyway, so that was Keats and Markov chains. The other process at work here, one I think is somewhat more interesting, is the recurrent neural network. So we've talked a bit about neural networks, or I have rather in other talks. Joyce gave a talk on neural networks, so I'm going to not spend a lot of time talking about machine learning or neural networks. I encourage you, if you're interested, to, if you didn't see her talk, I guess invent a time machine and go back and see it, or you can wait for it to come out on YouTube. So I'll add some details for color, but I'm not going to spend a lot of time on the fundamentals of machine learning and neural networks. Aside from, neural networks are very loosely based on biological brains. And I'll show a diagram in a moment, but recurrent neural networks, unlike feed-forward networks, the ones you normally see where there's inputs, hidden layers, outputs, or Markov processes which do not have memory, recurrent neural networks do. Later layers feed back into earlier ones, and so you get this sort of temporal dimension to your model. So this is what people will use to generate text. I gave a talk at Ruby Kaigi this year about generating music with Julian Scheel. The recurrent neural network is ideal for things like handwriting recognition, voice recognition, things like that. Anything where there's sort of a temporal dimension to the data that you either want to generate or predict. The library that I used, DL4J, Deep Learning for Java, you'll see some of the code, it is very Java-oriented, has a lot of examples, a lot of good tools for doing this kind of work. I'll talk about this a bit later. I do want to get to use Cortex or sort of a more Clojure-first tool, because when you do see a snippet of the code, it is not as idiomatic as I would like. And as mentioned, I switched from Keats to Shakespeare for this one, which is much larger. It's about 125,000 lines, close to 1 million words, and 5.6 million characters. And the reason for this was really there were not enough data in the Keats corpus to get meaningful, good results. The recurrent neural networks, it produced some things that were kind of Keats-ish, but it wasn't great. So that's one thing that you will find as you're tuning your machine learning models or working on anything with neural networks is struggling to get your data to be the right shape, to have enough of it, cleaning it up, et cetera, et cetera. So like I said, this is sort of the general structure of a recurrent neural network. Later layers feed back into earlier ones. And the way that training works in neural networks is you pass a signal through the network, the neurons have their weights adjusted. At the end you say, okay, this is actually what the deal was. The machine says, okay, I was off by this much, and then propagates or back propagates the error signal back through the network, adjusts all its weights, and trains again. So we do this with recurrent neural networks, and we do them in mini batches. And the output here would train on maybe 10 or 20 mini batches, produce a sample, train on another 10 or 20, produce a sample. And you'll see in the next few slides, it's truly fascinating how good, how quickly, and how good the results become and how quickly they become good. Having said that, I am now going to spend some time on a tangent. So I'm going to take a quick detour. We're still going to talk about recurrent neural networks, but we're going to cover two of my favorite, relatively recent applications. And they're both by a researcher named Janelle Shane, and I hope I'm pronouncing her name correctly. This first one is recipe generation. So these are the titles of recipes that a recurrent neural network wrote. And if you can't read them, I'm going to read a couple of them to you. Cream cheese soup. Cream of sour cream cheese soup. Chocolate cake. Parentheses, chocolate cake. Chocolate, chocolate, chocolate cake. Chocolate, chicken, chicken cake. Chocolate, 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 chocolate cake. Et cetera, et cetera. So this was after, I actually don't recall how many training cycles, but you can sort of adjust hyperparameters and tune things, and if you loosen things up a bit and let the machine not hew so closely to chocolate, I guess, or English, words it hasn't seen before start to appear, and words that nobody has seen before start to appear. So this is a little bit tough to read, but These ones are more imaginative. We have beef soup with swamp beef and cheese, chocolate chops and chocolate chips, crim grunk garlic cleese, beezy mist, export bean spoons in pie shell, top if spoon and whip the mustard, chocolate pickle sauce, whole chicken cookies, salmon beef style chicken bottom, star and then just an asterisk, cover meats, out of meat, completely meat circle, completely meat chocolate pie, cabbage pot cookies, which does sound like a thing, artichoke gelatin dogs, and crock pot cold water. So, so this is truly impressive. And like I said, the funny thing is how good RNNs become considering how bad they are when they start. So as you can see, these are just titles of recipes. And eventually, and this is kind of like how the RNN started to learn, is it would produce nonsense, and then titles, and eventually just endless lists of ingredients. But eventually it figures out the shape of a recipe, like the actual form of one. But early on, if you can read this, this is just nonsense. This was an early iteration. I don't think I see any words in there. There's a 4. Attempting to pronounce it, it's ui eb d1 ec nahirs egve ns, et cetera, et cetera. So its initial recipes are not very good. Over time, however, they become quite good. Pears, or to garnished meme, meats, 1/4 pound bones or fresh bread, optional, 1/2 cup flour, 1 teaspoon vinegar, 1/4 teaspoon lime juice, 2 eggs, brown salmon in oil, add creamed meat and another deep mixture. Discard fillets, discard head and turn into a non-stick spice. Pour 4 eggs onto clean, a thin fat to sink halves. Brush each with roast and refrigerate. Lay tart in deep baking dish in Chipek sweet body, cut oof with crosswise and onions. Remove peas and place in a 4 DGG serving. Cover lightly with plastic wrap. Chill in refrigerator until casseroles are tender. And ridge is done. Serve immediately in sugar may be added 2 handles over ginger or with boiling water until very cracker pudding is not. Yield 4 servings. And it's just amazing to me, the parts where it has seen enough of it to be like, this is what a recipe is. And then other times where it just kind of becomes inventive. But yield 4 servings is my favorite. Just this whole nonsense recipe. And I'm going to read you just one more. This one is very short. Coming back to Shakespeare, this is one I think is sort of maybe something Shakespeare might have had if all he had was weird gruel. 1/4 cup white seeds, 1 cup mixture, 1 teaspoon juice, 1 chunks, 1/4 pound fresh surface, 1/4 teaspoon brown leaves, 1/2 cup with no noodles, and 1 round meat in a bowl. And like I said, this is all Janelle Shane's work. There's a link to the bottom to her blog, which I think is, that's the Daily Dot, but her blog is on the next one. It's, I think, Lewis and Quark. So this is my favorite recipe. We're going to do one more before we come back to Shakespeare. So the same researcher, Janelle Shane, was told that there was a problem in her, I think she was in her, not her city, at least somewhere nearby. And the problem was they had a guinea pig rescue. And this is sort of sad. This kind of happens when you have sort of like a hoarding situation. They go and they clean out the home and they get all the poor pets and then they bring them to the guinea pig rescue and then people adopt them. And some people name their own guinea pigs. But it turns out that if you have a ton of them and you kind of want to keep track of which one is which, you just have to, as the rescue, name all of them. And they had so many that naming them individually was sort of onerous. So the rescue reached out to Janelle and said, hey, can you help name these? And she said, I have just the thing. So the recurrent neural network came up with guinea pig names. So this one gives it away a little bit, but that one is my favorite. So these are Pop Chop and Fuzzable. This is Buzzberry and After Pie. And my personal favorites are Flurry White and Stargoon. So I'm sure at some point I will, have a child and name that child Stargoon. And then they can watch this talk on YouTube and they'll know why. So all this to say, it's amazing how bad the neural network is at first and how good it becomes. And this is really kind of crazy. And both of these were done with a project, char RNN, by Andrej Karpathy. And he mentions he links to this project in a blog post called The Unreasonable Effectiveness of Recurrent Neural Networks, which I encourage you to read. It's a really great post. I love this quote, though, both the title and the quote. There's something magical about recurrent neural networks, sort of the meaning that we assign to what comes out, and sort of how good the results can be over time. So I encourage you, when you do have some time, to go and check out Andrej's blog, to look at char RNN, and to also look at the deep learning for J examples that we're about to go through. Anyway, that's enough random asides and tangents. We're going to come back to Shakespeare. Do you guys want to see what our RNN wrote? All right. It's not as good as the recipes, but it's still pretty good. Cool. So just to give you a sense, this is some of the code. So this is the configuration of the neural network. As I mentioned, it is very, very obviously Java interop. There's a lot of Java-esque names. The threading macro makes it a little bit nicer, but it's still not quite the way I like to write Clojure. So I'm excited, like I said, to eventually move on to projects like Cortex, or to have sort of a Clojure-first solution. So we'll talk about that a bit more, but that's hopefully in the future. So this first round from the RNN trained on the works of Shakespeare is after 10 mini batches. So as I mentioned, we do a bunch of batches, we see how we went, and we keep going. So it's a little tough to read, but I'll try to pronounce the first couple lines. Leufjend, Worcester, Antfatoimi, Noinsindius, Beloyalt, Thelveok, Theosir, Theorchenplad, my ard, etc., etc. Now, this is total nonsense. This is not Shakespeare. But it's fascinating to me that already, if you look at this, it already looks a little bit like part of a play. And I sort of fibbed to you a little bit. The Shakespeare corpus is far more plays than anything else, so this is going to be more of a play or a prose poem than a more traditional poem like a sonnet. But this is amazing to me that it is pronounceable. The network has already figured out how to stitch letters together in ways that sort of make sense. You get words, almost words, like Worcester. You don't get like 19 X's in a row or a bunch of numbers. It knows how to break words up into pieces. You have white space. You have words that are roughly 2 to 12 or 15 characters. This is almost like English already, at least in a very blurry way. And after those first two words, it uses a comma correctly for some definition of correctly. Like, it does know where commas go. They don't appear in the middle of words. It's really fascinating to me that even after this short amount of training, you get something that looks, from a distance, like language. Now this one is after 50 mini batches. Ast being blee earther, that is fey that hath a begwer, and the face. Exunt frauds, let linger me, Lothfie ernst with honors by thee. Gloucester, Henpley can cut these orward, plence was he likeness quince, det wilst of brother, he will setch the exate. Now this is almost English. We have things that look like sentences now. That is fey that hath a begwer. Like, you could imagine that fey and begwer are like weird Shakespearean slang that we just, I don't know what that means, but sure, this is a line from a Shakespeare play. It's almost a sentence. It's shaped like a play. You have now things that look like stage directions, exunt. You have Gloucester speaking. So after only 50 mini batches, we now have something that resembles the structure of a play and things that actually look like sentences that are not just pronounceable, but there are English words in here. And the face. Like, that is a weird exclamation, but it makes sense. You could say that, and the face. I don't know when you would say that, but that is a legitimate English utterance. Like I said, I'm just fascinated by how quickly this becomes pronounceable. Now this is after 160 mini batches, and this is what I think is really, truly amazing. Sylvia, the sleep villain, so shouty I desire, like his courtiers thrice of cursed, and forelady, doth be honouring broke of this, and so who lay subdue my comforts. Queen Elizabeth, where's Bougade? Or Bougiddy, or whoever. So this, like I said, this is truly, truly amazing to me. I feel like you could put this in front of middle schoolers and they'd be like, "Yep, that's Shakespeare." I don't know what it means, but I actually do want to see that experiment. I want to see somebody like run this and put it in, kind of slip it into the readers in middle schools or high schools, and people just kind of go through and say, "Okay, well, I wonder what this." I would love to see a paper about what this play is about. That's what I would like to see, either written by a human or another recurrent neural network. So. Honestly, I think, well done, right? Like, this is pretty solid. And again, it's almost, I think unreasonable effectiveness is how I would describe it. This is unreasonably effective. This training took a couple of hours on a 2012 MacBook Air with no GPU, just, sitting and churning and thinking, and it barfed this up. This was not run on a huge AWS cluster. This didn't take 2 days. It took a couple of hours with machinery that's years out of date. And I think the interesting thing about all of this, bringing it back to the discussion of poems about machines, poems that are machines or readable by them, when we sit down to tune neural networks, or build models, or write poems, or write Clojure programs, those are all the same thing. Those are the same process. We are stealing, we're collaging, we're making something that wasn't there before from parts that were. And I just find this really fascinating. And I would, if I had the opportunity, love to stitch together some kind of course or talk or series of poets and programmers together producing almost Shakespeare, from Shakespeare. So we're getting toward the end of our time. I'm probably going to talk for just about 3 more minutes, which means it's time for the summary, the TLDPA, or too long, didn't pay attention. So it's fine. So if you were not paying attention and you just tuned in now, you're going to get the whole talk in about 60 seconds. So we talked about poems about machines. We talked about poems that are readable by machines, and then looked at some poems, quote-unquote poems, written by machines, with a detour through guinea pig names and recipes. So as promised, I don't know if you saw the tweet, John Keats did say my name from beyond the grave, so that was cool. There was at least one guinea pig, which was great. We saw that poems are emotive programs, and programs are poems for the machine. These are one and the same. And that poems can be programs, and machines can write them, which is fascinating. So we saw Markov chains, we saw recurrent neural networks. I think in the future, what I'd love to do, I mentioned this before, is spend some time with Cortex, translate this code into something that's more idiomatic, easier for Clojures to look at and say, yes, I want to do that. If we want to do machine learning, if we want to write poems or recipes or who knows, I think Gilbert and Sullivan would be amazing. And we want to do it in Clojure, we have to build those tools. So we have some of them now. We have a lot of leverage in the Java ecosystem on the JVM. There's a lot of great libraries, a lot of great tooling. And I think the tools that we can leverage and the new ones we can write will mean that we get to do this kind of thing in Clojure all the time. And that's really what this is all about. So like I said, I think Cortex is the next stop for this. So thank you to Joyce for her talk yesterday. I think I had heard of Cortex at ClojureCon, not Conj, rather, Euroclojure, but amazing to kind of see the code and understand more about how it works. And my referencing her talk definitely does not mean that I finished these slides 61 minutes ago. So anyway, we are right around 34, 35 minutes. That's all I got. So. Slides will be up on SpeakerDeck. Code will be up on GitHub either later tonight or tomorrow. Thank you again for coming to my talk. I really do appreciate it. Thank you for choosing to spend your time with me. And if we have time for questions, I'm happy to take a couple. Yes? Lovecraft and Whitman, that's genius. So the question was, have I ever thought of mixing 2 authors? Yes. Actually, as I mentioned, there's a Ruby program I wrote a few years ago called Rukovsky. I trained it on a combination of my poetry and Keats, and it wrote some very fascinating poems. Then I trained it on my poetry, Keats, and Allen Ginsberg, and it wrote a poem that, to this day, one of my good friends still quotes the title, Jesus, the Bloody Toilet. That poem was not good. Yes? Mm-hmm. I would love to be the change I want to see in the code base. So if they don't implement RNNs and I can help with that, I would be delighted. Going once. Twice. If you have your hand up, please wait. Oh, yes. For things like, yeah, yes, that would be amazing, although I worry that there would be some liability in there. But yes, this is the kind of thing where you have like repetitive text, or I would love to see it write restaurant menus. If it can write recipes, it can write restaurant menus. I mean, you would probably get BZ mist or whole chicken cookies. But yeah, I think there is, or when I gave a similar talk at RubyKaigi about generating music, someone came up and said, hey, how do they generate like hold music now or elevator music? Is that something that in 5 or so years machines are going to do for us? I think the answer is yes. I think I can take one more question. Please wave if you have your hand up because my vision is terrible. All right, thanks everyone.